these experiences, have you ever noticed that when you get out of a car on a dry day and you touch the door, you suddenly get a shock?
Yeah, it has
Or taking
occurred to
off your
me.
clothes,
Yes.
yeah, you get a shock. So all these things actually happen due to something called static electricity.
Okay, sir. Static electricity.
Static electricity. And people realized all this happens because there are two kinds of a thing called charge. So there's this property called charge in nature, like other properties you already know, length,
Yes.
mass, time. So there's a new property called charge. And what is this? This can have two kinds of values, either positive or negative.
Hmm.
Some things can be positively charged, some things can be negatively charged. Although most things around us are actually neutral. The total charge on most things is zero.
Like the equal amount of positive and negative charge.
Exactly. Equal amount of positive and negative charges. So maybe you know something about an atom.
Yes, sir.
What do we know? In an atom, there's a nucleus.
Yes, in the nucleus there are positive and negative charge, and there are also neutrons.
There are neutrons, and there are only positive charges in the nucleus, and around the nucleus there are these
Yeah,
electrons which circulate,
electrons.
and these are negative. So in total, the atom is actually neutral. The amount of positive charge in the nucleus is exactly balanced by the negative charge of the electrons.
Electrons.
Positive and negative. So what happens is this new nucleons, you call them nucleons in total, the protons and neutrons, they are very tightly bound. And in real life, in usual day-to-day life, it's very hard to separate them out. It's only in the large hadron colliders and very large experiments that you can actually separate them out. So this neutron and proton, they are very tightly bound in the nucleus.
Hmm. Okay.
These electrons, however, especially the electrons in the outer shell, they are quite loose, and a little bit of friction is enough to separate them out.
Yeah.
And that is exactly what happens. When you are rubbing your hair with the comb, some of the electrons from the comb actually, due to the friction, come off from the comb and get deposited on your hair. And what that does is it suddenly breaks the neutrality that we have around us. There's suddenly an excess of excess of electrons on your hair and less electrons on the comb,
The
which
comb.
makes the comb positive and your hair negative, and suddenly they start attracting each other. Okay, so now we came to know that these charges attract if they are opposite and repel if they are the same. So an electron would repel another electron, but
Yeah.
an electron and a proton will attract each other. So similar charges attract. We say that likes likes repel and unlikes attract. That's good. So people devised a method to actually figure out how much charge is in something. Okay. So what they did is they took a metal ball and down here they put two gold leaves. You know gold leaf, rangta, that they put on sweets?
No.
Very
No.
thin gold
Sir.
foil. So what they do is, since gold is very ductile, you can actually beat it up into very thin sheets.
Hmm.
So thin that it's actually a few atoms thick. So they take those gold leaves and make a two leaves and put them together like this. And so this can be used to actually detect charges on things. How come? So suppose you put some charges on this, on the top sphere here. Because it's connected by a conducting wire, these charges travel onto the gold leaves, get transferred.
Okay.
And now since we know that like charges repel each other, so this part of the leaf and this part of the leaf starts to repel and they separate out. The more
Okay.
charge you put in, the more they separate out.
Okay.
Usually it's drooping down, but when you put charges, it separates. So that can be used as a measure of,
So if we also apply negative charge, it'll
it'll
occur.
do the
Okay.
same thing. It'll do
Okay.
the same thing. So that's how people used to measure charges. So it was called a gold leaf electroscope, and usually they put the whole thing inside a beaker because the gold leaf is very fragile, so that it doesn't tear off, and winds can also affect it. So they put it in a closed environment in a beaker, something like this.
Okay.
But we still did not know how much these actually repel and attract each other. These charges. We know that likes repel, unlikes attract, and so on. But what is the exact amount? So there came this scientist called Coulomb, who made it his work to actually figure this out. He did very meticulous experiments using something called a torsion balance. So you have this thing on your ceiling, you hang this string from your ceiling, and on the end of the string, you put a rod, a rigid rod, and on both sides of this rod, you put giant spheres, giant metallic spheres, identical, sorry, something like this. And then you bring in some charge. You bring in some charge, say positive charges, and since there was no way to measure these charges, you don't know what the amount of charge is. There is no way to measure at that time. So you just put some charge on this sphere, and put an equal amount of charge on the other sphere. How can you do that? How would you accomplish this? So
By oh,
yes, go ahead.
um, like there is conduction, induction, and this right friction.
Hmm.
So to apply just to have positive charge in the metallic sphere, we have to um, wait. Please explain, sir.
Sure, sure. So we want both of them to be equally charged.
Yeah.
It's easy to put one kind of charge. So people have figured out that let's call this one positive. It's just a convention. Let's call this positive and let's call
Okay.
this negative. So maybe the glass rod they started calling positive. So it's fine. So you put the glass rod in contact with these metal spheres and some of the charges get transferred. That's good. But how do you put equal charges on both spheres? So people figured out that symmetry can help you here. If you take two symmetric metal spheres and then you put some charge on this, doesn't matter what amount of charge, say capital Q, and then you bring the other sphere which is uncharged and you touch it with it, or you connect them with some wire. What happens? Some charges will start flowing
Yeah.
from this sphere to the other, because positive charges they don't like staying together. They repel each other.
Yeah.
So some of them will get transferred to this so that they are as apart as possible. And how much would it transfer?
An equal
If
amount with
an equal
the
amount.
with the first sphere.
Exactly. If these are identical spheres, it must be an equal amount because the charges don't know which sphere is which. They see the identical situations on both sides, so they'll equally distribute themselves. So this is a great way of using symmetry. So now you have got a q by 2 and q by 2 charge on both spheres. And now you can bring both spheres and touch them, touch one to this one, touch the other one to this one, and so you'll have a similar equal distribution of charges on both these larger spheres. So that was accomplished like this. Now, what they did is they brought some other spheres, some other charged sphere close to one of them. What does it do? It produces a torque on this whole system. So this starts rotating in this way. And this rotation causes some torsion in the string, which is supporting the whole system from the ceiling. And this torsion, people had figured out by then, using classical mechanics, how this torsion functions. So they know how much angular deviation means how much torsion. And this torsion can be used, this angular deviation can be used to very accurately measure forces. So they can firstly use q by 2 charge, then they can halve it again using another sphere, and then they can use q by 4 charge. And using these different charges, they figured out what the kind of forces these charges exert on each other. So what Coulomb found is that the force is directly proportional to not the charge, but the charge squared. And he
Okay.
also found out that as he started bringing these spheres together, that it depends on 1 by r squared. It's proportional to the inverse of the distance between the spheres.
Okay.
So the closer you bring them, the more repulsion they feel. And he combined these two. He combined these two into one law, called it the Coulomb's law. So F should be proportional to q squared by r squared. And if you uh, remove this proportionality and bring in an equality, you get something called a proportionality constant.
Yeah.
So it becomes
So
kq squared by r. Hmm?
so in this one, k is equal to 1 by 4 pi epsilon naught, right, sir?
Exactly. So there are historical reasons why he chose this particular number. We'll come to this. There is a specific reason for choosing this. And then he was able to generalize this law. Now see, the both charges were same, so he could generalize this when both charges are different. And again he did some very meticulous measurements, and he found out that when both charges are different, the force becomes 1 by 4 pi epsilon naught q1 q2 by r square, where q1 and q2 are the charges and r square is the distance between them. Now you might already know that force is a vector quantity,
Yes.
so it doesn't make sense to only tell its magnitude. You also have to know the direction of force to
Yeah.
do anything useful. Could be that the force is acting like this, or it could be the force is acting like this. So the magnitude doesn't really tell you much. You also need the direction. So what is the direction that he figured out? He figured
Uh,
out that this direction always acts along the line joining them, either
okay.
in this direction or in this direction, depending on the polarity of the charges. If they are the same charges, negative, negative, positive, positive, then they will repel and the forces act outwards. Whereas if it's attractive, the forces will be inwards.
Inverse. Okay.
So you can express this in terms of a vector. F force on 1 due to 2 is equal to 1 by 4 pi epsilon naught q1 q2 by r12 squared r12 cap. So this cap here, this signifies that this is an unit vector. And what are unit vectors? Unit vectors are vectors which have length 1.
Okay.
So r12 cap would be the same as r12 vector, but now you divide it by the magnitude of r12, so that its
Okay.
length becomes 1. And can you use Newton's law to tell me what the force on charge 2 due to 1 is? How is it related to this force?
Um. Will it be negative?
It will be negative of this. Newton's third law. Good. So now that we know what the forces between any two charges is, we might want to apply this to a situation where we have multiple charges. So even in a very simple system like the atom, there are multiple charges in the atom. So you'll have to figure out what the resultant force on something is. And how do you do that?
Resultant force.
Mhm. Suppose you have three charges on the three vertices of an equilateral triangle. Equal charges, Q, Q, and Q. And then at the centroid of the triangle, you place a small charge, small q.
Oh,
What force
I,
would it feel?
a centroid force. Something I have forgotten about it actually.
So the thing is, if you actually join these lines, they would give you the direction of the forces.
Yes, sir.
And since the situation, see, it's invariant under rotation of 120 degrees. If you rotate this figure by 120 degree, it returns to the same figure. Nothing changes. So the forces should also be equal. By symmetry, we can say that this force, whatever this is equal to this force, and this is equal to this force. All the forces must be equal in magnitude. Directions must be different, but magnitudes are same by symmetry.
Okay.
So this, what I did here is implicitly apply something called the superposition principle. What this says is, if there are multiple charges, we can just take two of them. We can take pairs of them, calculate the force using Coulomb's law, and then add to it whatever other forces it feels due to the other charges.
Okay.
So what this means is, you can only take any pair of them and figure out the force due to it. So that's what I did. So the total force must be the resultant of these three forces. By symmetry, you can see these three forces are symmetrically pulling it on all three sides.
Yeah.
You can also do a component analysis, x component, y component, and you'll find out that it exactly vanishes. The total force is zero.
Okay.
Okay, let us look at a bit more interesting problem. So we've got a situation like this. So here you've got sorry, a minus q charge. Here you've got a plus q by 2 charge. And here you've got a small charge, test charge q, on the same straight line. So the question is, if this distance is 1 meters between q and q by 2, at what distance must I place this small charge so that it feels no net force? So this is 1 meters.
What's messaging?
Could you give this a try?
Uh, so the remaining would be, it would be one or so.
How did you uh, figure that out?
Well, q the distance between the charges uh, are in what do you call it? From this midpoint are equal.
But the charges are not equal. See, this is minus q and this is small q. It could be something different.
Okay.
So
So
you
then,
work it out. You'll get an answer which is in terms of q's. So it won't be a real number. It'll have variables in it.
okay,
So let me help you out a bit. What you do is you first calculate the force due to this first charge here. You'll
okay,
get some force on this due to this first charge. So if you assume that small q is positive, you'll get a force in this direction. Let's call this F1.
Okay.
Similarly, with the second charge here, you'll get another force on this direction, F2. And these two forces have to be equal and opposite so that the
Okay.
total force is zero. Agreed?
Okay. Yes, sir.
So now I can use Coulomb's law to find the forces. F1, this would be minus q by r squared, and r, the distance is, see, this one is x and this is 1, so this is x plus 1, total distance x plus 1 whole squared. Similarly, F2 is q and q by 2 times distance from x to second charge to q is just x, so this is x squared. So now you can equate these two, q minus q by x plus 1 squared equals to, must be equal and opposite, so minus of q x squared.
Why
Most
is it
of,
why is it q by 2?
because the second charge is q by 2,
Okay.
so this force will be calculated based on this second charge,
Okay.
q1 q2 by r squared. So most of them cancel out. What you have is x squared equals to
No, x plus
2x
1.
squared or 2x plus 1 squared,
Okay, yeah.
or 2x squared minus x plus 1 whole squared equals to 0, or so we get two values of x. One is 1 by root over 2 minus 1. The other one is x equals to minus 1 by
Root 2
root 2
plus
plus
1.
1.
Okay.
So obviously it cannot be negative. Distances are not negative. So
So
this is
it's
the distance,
okay.
the first. So what this negative is actually telling you is you could have placed this charge on this side, here, somewhere here, and you would have found a point where this is also true.
Okay.
So this thing that we did, this is called equilibrium. And equilibrium is when the total force on something is zero. Now in Coulomb's law, we had seen that there was this constant here, 1 by 4 pi epsilon naught.
Yeah.
Let's look at that a bit more. This thing, epsilon naught, this is called the permittivity. Permittivity of free space. And then you had your charges q1, q2 by r squared. So this whole thing sometimes is just written as k.
Yeah.
Sometimes you'll find that some books use k. This k has a value of, you need the value of this to find out any approximate force. 9 into 10 to the, sorry, I'm getting some feedback. Okay. So could you tell me what the unit of this is?
Um, if
How do you figure
I,
out?
I I think so. It's something like um something. It has meters in it, right? Oh no, wait.
It
Um,
has.
yeah, meters. Then
I
Suppose you forgot. Suppose you
Yeah.
forgot. You don't
Okay.
know what the unit is. How do you figure this out? So any equation in physics, whatever the equation be, always has to be dimensionally consistent. What I mean is the dimension on the left hand side have to match the dimension on the right hand side. So you can just put in the units for everything else and this will just drop out of the equation. Let's see. So for force, you know it's newtons equals to, I don't know what this unit is. Let's call this x. For charge, charge has a unit which is called coulomb.
Yeah, Coulomb.
So you put in coulomb times coulomb, two charges there. And bottom, you've got r squared. So this is meter squared. All right. So x turns out to be Newton meter squared per coulomb squared.
Okay.
So this has to be the unit. Good. See, there was some talk about free space. So what? Why do we need free space here? What does it mean? It
Is
means
this
that this force.
it
Yes, go ahead.
good? No, it the free space means like the space between the charges of the object, like just in general the distance between the charges.
Mhm. This is the space between the charges is devoid of anything else. So that's why it's called free space. In the sense that it's vacuum.
Yeah,
So
like
this force formula only works in the vacuum. If it
okay.
were not vacuum, the force formula would change a bit. What you would have is F equals to 1 by 4 pi epsilon naught. And then there would be this epsilon r, which is the relative permittivity of your medium, whatever medium you are doing the experiment in. And then everything else would be the same. So in a medium, the force law would be something like this. So this is only in vacuum. So this permittivity, why is this called permittivity? Because this is the amount of force it permits in that medium.
Okay.
Hmm. See, if epsilon naught were to increase, the force would get decreased
Yeah.
because the denominator something is increasing. So it's the amount of permission it gives. Right. So do you know about the lines of force?
I have forgotten about it, sir. Like I have not been paying attention to the first lesson for a while now. Like I was mostly focusing on the second and third chapter of the syllabus.
Currently, let's see. Which is the second chapter?
The second
Current?
chapter was, I think, wait, um, I don't remember the chapter, but the third chapter was about the electric currents and all.
Okay. Second one must be Gauss's law or something. Okay, let's see. Suppose we have a positive charge here. So lines of force is nothing but a way to visualize uh, the effect it would have on surrounding charges. Any charge has an effect on the other charges surrounding it. And lines of force just tells you what the effect is. So if you were to place a small positive charge over here, what would it do? Suppose there's a small positive charge.
It
It
would
would feel a force due to this larger charge
it would
in
repel it.
in this direction, somewhere radially outward,
Yeah.
and it would keep moving away. So it will be repelled. Something here would feel a force in this direction. Someone here would feel a force, a feebler force in this direction. And someone very near would feel a very strong repulsive force.
Yeah.
So this thing is codified in the lines of force. So lines of force are uh, generated. So for a positive charge, it would be outwards. Everything goes outwards because a small positive charge placed near that would feel a outward force. So if I remove this, lines of force for a positive charge go radially outwards. So this tells you the path a small positive charge would take if you were to place it somewhere here. What about a negative charge? Can you guess?
The negative charge, uh, if there were positive charge around the negative charge would be attract, but if it was,
Right. So
if
everything
it
goes
would
inside,
attract, yeah, goes inside.
radially inwards. So these are the lines of forces if you have only a positive charge or only a negative charge in the universe. But what happens if you bring them together, bring them close to each other? That's an interesting situation. You have a positive charge and a negative charge, and they are close to each other. What would happen then?
Then it would connect, right?
Exactly. So, say you leave a very small positive charge here. It would start being repelled by this, but soon enough,
It will attract to the this
it'll get
negative.
attracted to this
Yeah.
and it'll bend and reach this charge. So, it's something like this, very near it. And the direction would be from the positive to the negative.
Yes.
And these lines of force would also bend. Sorry, the other way. Something like this. So, lines of force actually tells us a few things. The density of lines of force in any region of space is a measure of the amount of electric force that something would feel there.
Okay.
Okay. So if you see that here, number of lines of force is very less. So people won't be feeling much force, so charges. But when you go here, there's a lot of lines of force, very dense amount of lines of force. So the amount of force would be more. Another property is lines of force cannot intersect. Why
Yeah, I
is
can
that?
intersect. If it were to intersect, then the direction would be what do you say,
Ambiguous?
changed. So if
Exactly.
it cannot be intersect, and the what do you say, the force near the electron or proton is the strongest point there. It has the strongest force.
Right. So what is it telling me? Lines of force are telling me if I place a small positive charge there, what would its motion be like at that point? That's what the line of force is telling me. So what if it were to intersect? Then see, say a charged particle was traveling along this path
Hmm.
and it came to this junction where there is an intersection of lines of force. Now the charged particle is confused. Which way do I go? It cannot decide. So that
That's
cannot happen. It cannot go on both directions at the same time. So that's why this is physically not possible to have a intersection between lines of force. Okay. What happens if you bring two like charges together, say two positive charges?
then it would repel.
Lines of force would repel. Exactly. So lines of force going in the same direction tend to repel. The lines of force would go out like this. So this concept that charges have an effect around them, in modern physics, we like to think that nothing can really exert an influence out there without some intervening thing like extending out, because nothing can have an instantaneous effect. Einstein gave us this. So that's why we invoke the concept of an electric field. Whenever you place a charge somewhere, it extends its influence in space around it. And this influence can be thought of in terms of an electric field. A field is what actually acts on the other charges. All right. So you can think that whenever you place a charge here, there's this imaginary thing that is extending out of it, which actually influences the other charges around it. And
Okay.
this field is a vector quantity. And at every point in space, it is a vector valued function of space. If you put in input a space point, say x1, y1, it would give out a vector. Electric field output would be a vector. And what vector would it be? It would be the vector of force that a unit positive charge would feel just at that
Okay.
point. So you know the electric field at a point is the force on a unit positive charge. And we can use the force formula to calculate the field then. You just put F equals to 1 by 4 pi epsilon naught. You have a charge Q, and the other charge you put in 1 because it's unit
Okay.
by r square. So this
So
gives you the electric field. Yes?
okay. So then it would just be 1/4 pi epsilon naught into
Yes.
Q into R
Yes.
square. Okay.
And now you can start to appreciate why this 4 pi factor is brought in. See, you can do this. You can put the epsilon naught away and you can attach this with 4 pi r squared. Do you remember what this is the formula of 4 pi r squared?
Uh, I I have we have revised many times, but I don't remember it, sir.
Uh, think spheres.
Spheres. It
The surface of a sphere. What is
was
the formula of the surface
so.
area?
Oh, surface area. Okay.
Yes, this is the surface area of a sphere. So you see, if you put a charge in 3D space, the effect, whatever influence it has to die down as you increase the surface area of the spheres. No, if some physical quantity is spreading out of something, it has to die down. So you make a noise here. You make a noise, and the noise travels in a spherical wavefront, and
Yeah.
it's getting spread out on the
Yeah.
spheric sphere. The more farther it goes, the larger the sphere becomes, so it spreads out over an even larger area. This effect too spreads out like the same way. And since we live in 3 dimensions, the spread out goes as the surface area of a sphere. And that's why you get this 4 pi r square factor down here. Okay. Now let us see what the electric field due to a point charge placed something here. Point charge is like. So this is the x-axis, or the radial axis you could call it. R is the distance. So you see this turned out to be electric field equals to 1 by 4 pi epsilon naught q by r square. So what does it look like? The graph has a nearby, it's very high, whereas the farther out you go, the less the value gets. So the
Okay.
graph has this sort of a, so it goes like 1 by r squared.
Okay.
Other parts are just constants.
So the same would be applied for a negative.
Exactly. Negative 1, the field would be negative. So there's a minus sign here on top if the charge is negative.
Okay.
So the fields would be like this on the
Okay.
negative side. You can also find the electric field due to multiple charges now using the superposition principle. You find the field due to each of the charges and then you add them up at a particular point. Electric field at a point due to multiple charges. Let us bring back our equilateral triangle and let us place some charges. Now one of them is positive, the other guys are negative.
Hmm.
Say this is plus q and these are both minus q's. Minus q and minus q. Suppose I tell you to find the electric field at the centroid, exact center of this triangle. So the field due to this point minus q is along this line towards this direction. Similarly, this would have the same thing along this direction, and then the positive charge on top will have an electric field in this direction.
So
Mhm.
in this, the directions for only for the positive. This what do you say? The positive charge it will remain positive,
Mhm.
while the negative charge will turn negative for the force.
Exactly. The field is due to a unique positive charge placed at some point. So the negative charges would attract this unique charge. So it will be attractive for the negative ones.
Okay.
But for the positive, it's repulsive. So now to find the total force, total electric field at this point, the centroid, you have to add these three up. And you must remember how to add vectors.
Uh,
Do you remember vector addition?
Not clearly.
So you'll need that. Let's see. Let's do a refresher. So there were two ways of adding vectors. One was called the parallelogram law, the other was called the triangle law.
Yeah.
So if you have two vectors, you have to add a and b, let's say. Then you complete the parallelogram. You take a side which is parallel to a and take a side parallel to b, and this diagonal then, leading diagonal, gives you the resultant. This is a plus b.
A plus b equals to r, right? Or some other.
Yes. Now, if you need to know the magnitude, you have to write this a plus b mod, which
uh,
means the length.
Okay.
This is equal to root over of a squared plus b squared plus
Plus.
2ab cos
Wait.
theta,
Yeah.
where theta is the angle between a and b.
Okay.
This angle is theta. So that's good. But do you remember Cartesian form of a vector?
No, not Cartesian.
So what we could do is we could reverse the process. Here we had two vectors and we added them up into one vector. We would also have one vector and split it up into two vectors. That is called a resolution of vectors. That's splitting up of vectors. It's called a resolution, and it's very helpful to resolve it into Cartesian coordinates. What you do is you take your usual xy axis, and the vector you want to resolve, you put it here. From the origin, you put the vector.
Okay.
Now this vector, you'll have some, you can drop a perpendicular from the top onto the x-axis. The length of this intercept you call the x component of the vector, Vx. Similarly, you can drop another perpendicular onto the y-axis. You call this the y-intercept, Vy, y
Okay.
component of this vector. And then you can write this vector v as the sum of Vx I cap
Plus.
plus Vy j cap.
Okay.
And what are these I caps and j caps? Like remember I said unit vectors?
Yeah.
Cap means a unit vector, so these are unit vectors.
Hmm.
But now I cap is a unit vector along the x-axis, and j cap is a unit vector along the y-axis.
Y-axis.
So you can represent any vector as a sum of something along the x-axis plus something along the y-axis. So this is called the Cartesian form. And you'll see that this form will be very helpful. So how do you actually find these values of Vx and Vy? We use a bit of trigonometry. If you know the angle theta here, we can use a bit of trigonometry. So Vx would be V cos theta, and Vy would be V sine theta. How do we get that? We get that from the basic trigonometric ratios. So what was sine? Say you've got
Sine.
an
Sine is
perpendicular
half.
by hypotenuse,
Yeah, perpendicular by hypotenuse. Then for cos, it's this, right? Base over hypotenuse.
base over hypotenuse, and tan was perpendicular over base.
Yeah, perpendicular over base.
So we just use that. So cos of theta would be base, which is Vx, over hypotenuse, which is V. So Vx over V, this must be cos theta. So Vx turns out to be V cos theta.
Okay.
The same thing for the Y. So we use a bit of trigonometry to figure these things out. And we can now actually apply this to our problem. See, this was an equilateral triangle, and that was deliberate so that the angles are known. These angles are all 60-degree for an equilateral triangle. And now these lines, which are the medians, they exactly bisect these angles into 30 degrees. Okay.
Yeah.
So what angles would this be? This one.
This would be 30.
So see,
No, no,
in
no.
this
Wait.
triangle, this one is
Uh,
30.
yeah, that is
This
30.
is a 90. So
So
this is
60.
must be 60.
Yeah, 60, 60.
So let us find out this uh, this vector's components along the x and y axis.
Okay.
So on the y-axis, this would be component, this one, and this would must be this vector times cos 60. So let us name these vectors first. Let us call, since the magnitudes are the same for these two, for all three vectors in fact, because the charges are exactly the same. The magnitudes are, let's call them E. Let's call the magnitude E.
Okay.
So this must be E cos 60. And what is cos 60? Do you remember?
Cos 60 is,
Half,
yeah, half, 1 by
half
2.
1 by 2. So this is E by 2. Similarly, this guy, this fellow here, also has a y component, which is the same, E by 2.
Yeah.
So both of them add up to give you a y component of E.
Okay, yeah.
And we
E.
also had this red guy, which was already E. So the total y force in the y direction is Ey is equal to twice E. 2 half
Okay.
E's and then 1 E totally.
So yeah,
So it's
2E.
2E. Whereas in the x-axis you see from symmetry that whatever this component is, this component matches it and exactly nullifies it by symmetry. No?
Yeah.
So there is no x force. Ex equals to 0. So the total force is along the y-axis downwards. Total field, I should say. Total field is 2E in the
2E.
downward y direction. So
Okay.
in vector form, you would write E equals to, the vector E equals to twice E into minus j cap, since it's in the downward y
Down,
direction.
yeah.
And now we can replace E. The electric field E at this point is q by 4 pi epsilon naught r squared, where r is the distance between the center and the corners. So you can write 2q by 4 pi epsilon naught r squared minus j cap. That's your answer.
Okay.
Now, since we have forces, we can think of doing some work with these forces. So that's where the idea of a potential comes from. You remember potential energies from
Yes, sir.
classical mechanics? So
Yeah,
that's where,
potential energy.
so voltage is the same as electric potential, and what it tells you is what is the amount of work that needs to be done on a unit charge, unit positive charge. So you'll keep getting this repetition of unit positive charge throughout the chapter. Everything is defined in terms of unit positive charges.
Hmm.
So what is the work that I need to do to take a unit positive charge 1 plus 1 from point A to point B? What work do I need to do? That work, this work I call the voltage difference between A and B, VAB. So for your home supply, you see that this 220 volt mains we
Yeah.
have,
Yeah.
this actually tells you the energy that
Yeah.
uh, or the work that needs to be done to take this positive charge from one terminal to the other. So you have got two
Okay.
prongs. So if you want to take this, you'll have to do 220 joules of work. So voltage is nothing but a work done. So work done has units of joules, we know.
Yes, sir.
And now I'm talking about work done on a unit positive charge, unit charge. So this is joule per coulomb. So for each coulomb of charge, you have to do this much of work.
Okay.
So this is the unit of voltage. So do you have any questions?
Um, Not really, sir. You have cleared my doubts.
That's good. We have some more time. Let us do a topic called dipoles.
Okay.
Dipole is a combination of one positive charge and a negative charge placed very close together. And this distance here, this one, we call this twice A, so that the half point is exactly A distance apart from both of them.
Okay.
For a dipole, there are two things that are important. One is the axial point and one is the azimuthal point. What are these things? Axial point is anything that lies along this axis of this dipole.
Okay.
This point is an axial point. And you could also take a perpendicular bisector of this dipole. Any point on this perpendicular bisector is an azimuthal point. So it's important to know what the electric field due to a dipole is. Why? You might ask why? Why this special combination of charges? Why do I need to know? It's because in most ionic solids, say sodium chloride, potassium chloride, the ions actually become small dipoles. And if you were to understand the physics of these solids, you have to think in terms of dipoles.
Okay.
The electric field in those solids are like dipole fields. So
Okay.
it helps to know what these are, what the field at an axial point is, what the field at an azimuthal point is. So let's look at the axial point. Let's say it's at a distance of r, this point. What's the field? Electric field, we'll use the superposition principle. Total electric field must be the sum of electric field due to the positive charge plus the electric field due to the negative charge.
Yeah.
And the charges are, say, plus q and minus q. So the field due to the positive charge would be q by 4 pi epsilon naught r squared. But here the distance is r plus a. This extra distance is a. So from the positive charge, this is r plus a whole squared. The negative charge, however, would produce a negative electric field. So minus q by 4 pi epsilon naught. Now the distance is a bit closer, so it's r minus a whole square.
Okay.
And now you take everything common and you do some algebra. Pi r square minus a square whole square. This is the a plus b minus b formula I used.
Yeah.
And top here you've got r minus a whole square minus r plus a whole square. R square minus 2ar plus a square
Square
minus
is r square
2ar
to
minus.
ar,
So things cancel off. R square
where a square.
minus a square. So what
So
remains is
it's minus 4 ar.
minus 4 a r q by 4 pi epsilon naught r square minus a square whole square. Now remember I said that the distance between the dipoles is the charges is very small.
Yeah.
We like to think that the distance is so small. Say you've got a sodium chloride atom. This is
Mm.
very small. It's a few Armstrongs, very small compared to this small r here. So that we actually say that r square minus a square, this is very much equal to r square.
Okay.
All right. So that approximately this turns out to be a r cube by 4 pi epsilon naught r to the fourth. And there's a cancellation. So you get your final 4aq by 4 pi
Pi
epsilon naught.
epsilon naught r cube.
So for a usual charge, you saw that the force fell off as 1 by r square. But now you see for a dipole, the force falls off faster at 1 by r cube.
Okay.
So this effect is called a shielding effect, because there are
Okay.
two charges, both of them shield the influence of each other. Now conventionally, we call this minus 4aq factor. You take minus 2aq, not minus, plus 2aq, you call this the dipole moment P. Okay, it's customary to write this as that, so that your expression becomes 2p by 4 pi epsilon naught r cube. And this p here is actually given a vector property. So the p is from the negative 1 to the positive 1. So negative, positive. This is your direction of p vector. And so you can actually put the vector here, and this will give you your electric field as a vector. Fine?
Yes, sir.
Okay. Let's stop the demo class here.
Okay. Thank you, sir.
Okay, good.